In this recording, I'll go through several conceptual questions dealing with electrical field and electrical force. Now, let's start with this one. What we do, we have two identical charges, a positive charge here and a negative charge here, and along the line joining us in the right side of the negative charge, we have a point B, just a location. And the question is, what is the direction of the electrical field at point B? For a situation like this, what we need to look at is the electrical fields due to each of the charges. The electrical field due to the negative charge is going to point inwards towards the negative charge. For example, at point B, due to this minus charge, I'm going to have an electrical field pointing this way. Now, the electrical field due to a positive charge will point, let me draw it in the right place, sorry. Okay, just to make sure that I'm not, it should be inwards towards the charge. Now, the electrical field due to the positive charge, let me choose another color, should point away from the positive charge. Away from the positive charge will make it like this. Now, however, the electrical field due to the negative charge should be larger than the electrical field due to the positive charge, and that's because the electrical field depends on the position, and the positive charge is much further away than the negative charge from point B. And remember, the electrical field, the expression is K Q over R squared. So since I have a much larger R for the positive charge, that means the red one is much smaller than the black one here in terms of electrical field. So the overall electrical field should point towards the negative charge, so it should point towards the left. And that's my correct answer. Okay, now let's discuss this question. What about at point C? Okay, again, we have a negative charge here, the blue one, and a positive charge, the red one. Now, the electrical field, point C is halfway between the charges, by the way. I'm not sure if the graphic shows it that way, but it's supposed to be halfway. Now, the negative charge is going to have an electrical field pointing towards it. So let's go blue color. So it's going to have an electrical field pointing towards it. So this is the electrical field due to the negative charge. Now, however, for the positive charge, the electrical field is going to point away from the positive charge. And that's going to be like this. I meant to choose red, but anyway. These two electrical fields are to be equal in magnitude, since we are the same distance away from the charges, and since we have the same charge magnitude. Remember, E is K Q over R squared. We have the same R and the same Q for both of them, so they should have the same magnitude, but both of them pointing towards the right. The one due to the positive charge, the orangish one here, and then it's pointing away from the positive charge, and the one due to the negative charge is going to point towards the negative charge. Okay. Now, what about at point A? And again, the line, the Y axis here is midway between the charges. So let's see if we can do a better job with colors. Now, the electrical field due to the negative charge is going to point towards the negative charge. So what I'm going to do is draw the line, joining the charge to the point, and draw the arrow pointing towards the charge. So this is the electrical field due to the negative charge. Now, in the case of the positive charge, the electrical field should point away from the charge. So if I draw the line joining them, so the electrical field should be like this. And again, these two electrical fields are equal in magnitude, which means their vertical components are the same and their horizontal components are the same, which means that my overall electrical field, the vertical components cancel since they are the same in magnitude, and we get an overall electrical field in this direction. So the answer, it is towards the right. Okay, what about here when we have two positive charges of equal magnitude? Okay, now if we have two positive charges, okay, drawing the line joining the charge to that point, and then drawing the electrical field. It's away from the charge, so due to the charge to the left, it's going to point this way. Due to the charge to the right, it's going to point this way. So the overall electrical field, kind of completing my parallelogram, should point this way. So it is pointing up. Remember, they are equal in magnitude since we have equal charges and we are at the same distance away from the charges. Okay. Now it's a different kind of question. So we have a negative charge at point A, and we have an area here, the yellow area, an area where the electrical field is uniform or constant. And the question, what direction does the force on a negative charge at point at point A point? Excuse me. Let me try to say that again. In what direction does the force on a negative charge at point A point? Now, so this is my charge. This is the direction of the electrical field. What we know is F is QE. Now, if the charge is positive, F and E point in the same direction. If the charge is negative, F and E point in opposite directions. Now, E is pointing towards the right. The charge is negative, so that means the force is going to point in the opposite direction, which is, in this case, to the left. Okay. This is an interesting question. We have an uncharged conducting sphere that I'm pointing to here. It is hanging next to a charged sphere. That's the red one here. What happens when the uncharged sphere is released? Okay. Now we have uncharged, meaning I have equal number of positive and negative charges, and then I have a charged sphere. Now remember, this is made up of a conducting material. What does that mean? The minute we put it nearby, so this is my sphere. What's going to happen to my sphere? The charges that are the same as the charges in the red sphere, oops, I always have a problem choosing this red color, are going to be pushed away to the other side of the sphere. Now, the charges of opposite polarity than the charge of the charged sphere are going to be in this side. So what does that mean? That means I have an opposite charge on this side of the sphere and the same charge on that side. It means, because I have opposite charges, that the sphere is going to get attracted. Okay. Now, here we have a different story. We have an uncharged sphere. And you see the graphic here, it's better than the one I did last time. When it is close to the charged sphere, this side is blue and this side is red. This is the opposite charge, and that's the same charge as the red sphere. And this one here is a grounded sphere, meaning we have a big reservoir of charges that we can get to. Now, so this sphere is going to be attracted to this one. What's going to happen when it is going to be attracted to this one? So eventually, it's going to touch it. When it's going to touch it, what's going to happen? Both of them are going to have the same charge. Okay. Once they have the same charge, what's going to happen? This one is going to be repelled. So when it is going to repel, what's going to happen? It's going to eventually touch the grounded sphere. What's going to happen when it touches the grounded sphere? It's going to give up its excess charge, and it's going to become neutralized. Once it is neutralized, we come back to this same situation. And same situation, it will be attracted again, collect extra charge, be repelled, get neutralized again by connecting to the grounded sphere, and so on. So it's going to keep on doing that back and forth motion. It's somewhat like an engine, until the charge here is dissipated, or the charge becomes too weak to be able to attract this enough for it to touch it, or to repel it enough for the sphere to touch the grounded sphere. So we are going to have an engine running till we use enough of the reservoir of charges that we have in the red sphere. Okay. So let's see. We have a negatively charged rod. It's used to charge an electroscope by induction. What is the resultant net charge on the electroscope? Whenever we charge something by induction, we get the opposite charge of what we approach to the electroscope. So without any analysis, we can say it's going to be positive. Okay, let's do an analysis anyway, just to explain, to make sure that we understand it. Okay, so this is my electroscope initially. And then we are going to approach. Okay, let me make the negative blue in this case. A negatively charged rod. So what's that going to do? What's that going to do is move negative charges here, and then leave the top somewhat bare of negative charges, so it's kind of positively charged. Now we approach a finger. That's the way we do, or we ground it. That's what we do when we charge something by induction. In this case, what's the ground going to do? It's going to try to neutralize the electroscope. So it's going to bring in this case, positive charges to neutralize these. Actually, what happens in real life is those excess negative charges, instead of staying here, are going to seep out to ground. But it's the same effect. So what do we have? So what we have a neutralized bottom and excess positive charges on the top. And then we remove the connection to ground. Let's see, remove the connection to ground. Let's see if we can remove those charges. So then the bottom is neutralized, the top is not neutralized. The ones that are neutralized we can... Okay, let's see. We removed more than what I want, but I'll redraw that. So this is what we are left with. Neutralized bottom and then excess red charges on top. Now when we move this away, then those charges are going to spread out evenly. Okay, and the veins essentially spread out. Okay, so we left there a net positive charge. Okay, let's see this next question. If the conducting electroscope were replaced by an insulating ball and then charged by induction as above, what would be the net charge on the ball? So what they are telling us, what if I bring a negative charge next to an insulating ball? So what's going to happen if I have an insulating ball? Now, if that's negative, what I'm going to get is, let's try, it's going to be difficult to do it with colors, but I'll try to do it anyway. So let's go back to, I don't have a good blue here, but this is the negative charges. So what's going to happen, I'm going to have negative charges throughout like this. And then positive charges. Remember, each negative charge is not going to be able to move away from its atom. So it's going to just reorient around the atom to be furthest away from the negative charge, but it's still going to be stuck in place. Now, if we connect this to ground, ground is not going to be able to do much because these charges are not mobile. They are stuck in there. So I connect it to ground. There are no charges that are going to come in to move into the insulator. So I can move the charge away and I get back to zero charge. Or not get back, because the whole time the charge of the sphere is going to remain zero. Okay, the last question of this recording. What we do here, we have two charges and we have the electric field lines around them. Okay, it's not a very good graphic, but we see here arrows coming out. And arrows like this. And it's asking us if the charge A is positive, negative, or unknown. Whenever the electrical field lines are radiating away from a charge, the charge is positive.